So Le Chatelier's principle states that, okay, if I have a state of equilibrium where the forward and reverse reaction rates are the same, if there's a change in conditions, that's going to upset the balance. Okay, so if there's a change in the system, that's going to upset the balance. Okay, so a system under some stress is going to shift to relieve that stress. Okay, we can go to the club. You know, I mean, this is kind of a silly. You got your club, and you got a line, right? And there's a maximum capacity of 300, you know, and you got people on the line. But all of a sudden, I don't know, there's part of the club that's closed, and now the maximum capacity is only 250. So that's going to cause what? 50 people to move on outside, right? That's a stress on the system. I could fit 300, but now I have less room. I can only fit 250, so it shifts to the left. It moves 50 people outside. That's similar to what Le Chatelier is saying with reactions. There's some stress. There's going to be a shift to kind of relieve that stress. If I can only fit 250 people in the club and there's 300, I'm going to have to kick 50 people out, right? So there will be a change in the rate of the forward or reverse reaction at first to change the system back to an equilibrium. So if there was only 250 allowed, at first the reverse reaction is going to be greater than the forward because I need to get 50 people out. But once equilibrium is reestablished, then it would be the same. As 2 people leave, 2 people can go in. But I first have to reestablish equilibrium. So let's look at this situation, right? What would happen to the system if I add more reactants? Okay, so I've already established a dynamic equilibrium in a closed system. I've produced products, and we've reached the state where the amount of products and reactants don't change, and their rates are the same in both directions. But now I put in a bunch of reactants into the system. Well, if I add more reactants, we already talked about the effects of adding things and increasing concentration. If I add more reactants, there's more reactants that are going to be colliding. If more reactants collide, the forward reaction is going to go up, and I'm going to end up producing more product. So this is going to give me a new equilibrium concentration. Okay, so they're going to reestablish their equilibrium. So at this temperature, they come up with the same constant, right? So if I add more in the denominator, right? If I make the denominator bigger, well, there's going to have to be a shift so that the numerator, the products, is bigger. The only way to do that is if there's a stress of increasing reactants, well, I have to have more collisions, right? And that's what happens, so that I can produce more product. So the effect of adding a reactant shifts this equilibrium, what's called to the right. The reason why there's a shift to the right is because I need to make more products to reestablish this constant, right? So if my denominator goes up, I need to make more product so that it can equal what it originally equaled. The only way I can make more product is if my forward reaction goes up. So that's kind of like, right, if I can only fit 250 people in the club, I need to get 50 people out quick. So that, in that example, the reverse reaction would happen faster. Well, here, the forward. Now this, a lot of students do not like this. They hate this concept. I don't know why. So what I tell people is I have a really, it's kind of a dorky little trick, but you can think of it as, I call it the trough example, right? Now, what do I mean by trough? Right? I have 2 sides and I have water. Okay, so I have water on both sides, two separate troughs, and they're connected with this tube. Okay, and equilibrium, you could think of it as the water is going back and forth at equal rates, kind of like equilibrium. Does that make sense?
Yes.
Thank you. So equilibrium means the movement in the forward and reverse direction are the same, just like if I had two troughs of water connected with a tube. Well, what would happen, right? What would happen if I have more reactant? You could think of it as, if I have more reactant, I'm pouring more water on this side. I'm increasing the water level on this side. So what would happen to compensate for that increase in water? What would happen?
The water would flow through that little trough area and fill up the other side, or like try and be equal.
Exactly. So to compensate for the increase of my, level on this side, what is it going to do? It's going to shift to the right. So if I increase reactants, that's like pouring water in on this side. There's going to be a shift to the right to compensate for that level so that eventually they can get and reestablish a new equilibrium with new concentrations to get that same even flow back and forth. Okay. Well, what would happen if more product was added to the system? Right? So what happens if there's more product? Is more products are going to collide. And if more products collide, I'm going to have more collisions for the reverse reaction. And if there's more collisions for the reverse reaction, right, I'm going to form more reactants. So the effect of adding products shifts it to the left. Well, so a lot of people, again, they struggle with this. So I always tell everybody, do this. Draw a trough. Draw a double trough, right? It's connected, right? We have a state of equilibrium where the flow is equal. But if I add product, it's like pouring more water on the side. I'm adding more water. So how is this stress of adding more water on the product side, how is it going to be mitigated? How is it going to be relieved? What type of shift am I going to see if I'm pouring water on this side? Anybody?
Shift to the reactant side.
It's going to shift to the left, right? Because as this rises, water is going to flow this way to help compensate for it. Does that make sense? So this is my own analogy, by the way. You won't see this analogy in a lot of places, but I think it's quite effective. It really helped me with equilibrium. Are there any questions with that? Like kind of thinking of it in terms of flow, right? If I pour it on the right, it's going to compensate because now I have more collisions of products and I'm going to have more collisions. So the reverse reaction is going to occur more frequently than it did before until this level gets bigger, right? And because if I have the reverse reaction increasing, I'm going to form more reactants, and eventually these levels will balance out again and I'll reestablish my equilibrium. But once there's that stress, there has to be a shift. And you have to be able to identify that shift. So Le Chatelier basically states that if some stress system, it's going to cause a shift in either the forward or reverse reaction or reactions to compensate for that shift and reestablish the equilibrium. So the equilibrium constant comes out to be the same. So we saw that with the earlier examples. So now our discussion is, well, what would the effect of a catalyst do? We know earlier that catalysts lower the activation energy by providing the correct orientation for bonds to break and bonds to be formed. So it increases the rate of the forward reaction. We know that to be true. We see it with enzymes, and we see how it speeds up reactions. But the catalyst, right, it also lowers the activation energy for the reverse reaction as well. So it increases the rate of the reverse reaction as well. It's both. So it increases the rate of the forward reaction, and it increases the rate of the reverse reaction. So what it does just decreases the time it takes to reach equilibrium, but it really has no effect on it. So a catalyst is not considered a stress on a system, right? So adding reactant, that causes stress. Adding more product, that causes stress. Adding a catalyst, all it does is lower the activation. So it doesn't cause a stress. It just speeds up the process of reaching equilibrium and reaching the point where the forward reverse reaction rates are the same. So when we were writing out our equilibrium constant expressions, we were putting in to those expressions gases. So we've recently talked about the gas laws and how, decreasing the volume of a gas increases its pressure, right? Because pressure is proportional to the number of collisions. Decreasing the volume would increase the number of collisions, and increasing the number of collisions causes more pressure. So when a reaction at equilibrium has different moles of reactants and products, a decrease in volume is going to increase the concentrations, upsetting the equilibrium, and we're going to have a shift where there are fewer moles. So I look at it as, if I look right here, right, here are my reactants. How many moles of gas are there? Well, there's 1 plus 3. There's 4 moles of gas. And on the product side, there's 2 moles of gas. So I don't really, more moles. Okay, I don't really like this right here. So I'm going to go back. What I like doing, let me go back on that. I'll use the trough again. And we can look at it this way. If I decrease volume, okay, and I don't even need the trough here, actually. If I decrease volume, okay, that's going to increase pressure. I'm going to want to relieve that pressure. So I'm going to shift to the side that has fewer moles of gas, right? Because when we talk about gas, we had mentioned earlier that the identity of the gas doesn't matter. All that really, it doesn't matter what type of gas. All that matters is the number of particles and how many collisions there are, right? So if I have more particles in a container, there's going to be more collisions and there's going to be more pressure. Well, if I decrease volume, right, there's going to be more collisions and more pressure. So if I decrease volume, how can I decrease pressure? I have to figure out a way to decrease the number of collisions to compensate. So how can I decrease the number of collisions? I'm going to shift to the side that has fewer moles of gas. So which side has fewer moles of gas? The reactants or the in this particular reaction? Not all reactions, but in this one.
The products?
The products. So if I decrease volume on this container, right, I want to have fewer particles so that there's less pressure. Well, the only way to have fewer particles is to go to the side that would result with fewer particles. So what side has fewer particles? The products, there's only 2 moles. So by decreasing volume, I see a shift to the right. What would happen if I increased volume? Right? If I increase volume, what happens to pressure? That's Boyle's law, folks, gas laws. So that's something maybe, you know, if you're not sure, you can watch the video but if I increase volume, so now I take the same number and I put it, right, in a bigger container. What happens to the pressure? What happens to the number of collisions?
It goes down.
Goes down. So, well, I don't want pressure to go down. So how am I gonna compensate for an increase in pressure? I have to increase the number of collisions to increase that pressure, to reestablish that equilibrium. Because increasing the volume was the stress, right? It caused a decrease in pressure. I have to alleviate that decrease in pressure by increasing collisions. So how would I do that? I would have to shift to the side where there's more moles of gas, because more moles of gas are going to increase the number of collisions and reestablish the initial pressure. So that's why some people, it's a little tricky with the Chatelier's principles. You can also see it in the case with heat, right? So earlier this semester, we talked about endothermic and exothermic. So an endothermic reaction, right? How do we write out the enthalpy of that reaction or the heat? Was it a positive or a negative sign? If it's endothermic, entering, is heat positive or negative? Anybody? So no one knows? So heat of reaction, Q. We did this with stoichiometry, the heats of reaction. We did this with our stoichiometry section, right? Which is chapter 5. And then we also did Q, I think in chapter 3, Q equals MCAT. And because remember, the final is cumulative, right? So Q equals MCAT. What was endothermic? Was it a positive value or a negative? If heat has to enter a system. So to boil water, does heat enter the system?
It would be positive.
Yes, to boil water is an endothermic process. Why? I have to put heat into the system. When I put heat into the system, what happens to the temperature? Goes up and increases. My final temperature is higher than my initial, so it's a positive value. Endothermic reactions are positive in their value. So they're written on the reactant side, okay? So if you have an endothermic reaction, it's written on the reactant side. A decrease in temperature removes heat and shifts it towards the reactants, right? So if I decrease temperature, it's going to move to the side where the temperature is located, where the heat is located. So an increase in temperature is going to shift it to the right. Now, you might not like that. So here's a way to look at it. You can draw a trough. Here goes the trough. I'm going to treat the heat, because this is endothermic, as if it was a reactant. And if I have a trough where this is connected, okay, let's look at If there's a decrease in temperature, the heat is on the side. A decrease wouldn't be pouring water in there. It'd be like taking a bucket and taking water out. I'd be pouring water out. So if I pour water out and this side lowers, what kind of shift would I see? Right, if this side starts lowering, because I'm pouring water out, and this side starts getting lower, how is this trough going to compensate to adjust for that new level?
The flow from the right side is going to adjust and
Yes,
go to the left side.
So I'm going to shift towards the heat, right? So if I'm losing heat, temperature, if I'm taking heat out of the system, I'm going to shift towards the reverse reaction where the heat's located, right? Now let's do the other example, right? Let's say I add, whoops, I really don't like that, but let's say I increase temperature. Well, where's the heat located? It's on the reactant side. So increasing heat is like putting heat into the system. If I add more heat, which reaction is going to be driven? The forward or the reverse? So if it's an endothermic reaction that requires heat energy, and I increase the heat, what's going to be preferred? The forward or the reverse? I'm pouring water on this side. It's going to flow that way.
It'll flow forward.
Yes. Right. So what if it was different? What if I had, and I can make it different. Let's say I had reactants. I had an exothermic reaction. Okay. Say I had exothermic. Is that a positive or a negative value? Heat is exiting, losing. What does that mean?
Negative.
It's a negative value. Okay. Where would we write it, right? If we had equilibrium, would we write it on the reactant side or the product side? If
On
I'm
the product side.
because I'm losing heat. Okay. So same thing, I could draw two troughs, right? But now the heat is on the product side. If I add heat, where would it be like pouring water? Would it be pouring water on the reactant side or on the product side for an exothermic reaction?
On the product side, and the flow would go towards the
So
left side.
it'd be like pouring the heat that, and it would cause a shift that way. So an increase in temperature would pour it on the side of the heat and shift it that way. That's the opposite of what we were just doing, right? If I clean this all up, okay, right? If I add heat on this side, if I add heat on that side, it'd be adding it on the reactant side. Why?
The flow.
It's endothermic. So
pushing-
there'd be a shift to
yeah.
the forward. There'd be a shift to the forward. If I'm exothermic, the heat is on the product side. If I add heat, it's going on this side, there'd be a shift to the reactants.
Well, that makes sense.
The trough is, I mean, it may not seem it, but it's actually quite useful. Now, what if I decrease temperature, right? So here I have an exothermic. I decrease temperature. How is the system going to want to create heat, right? Right? I'm taking heat away from the system. How is the heat going to, how is this equilibrium going to compensate for this temperature?
The opposite side is
Decrease.
going to
It's going to shift to the right. Why?
right Yeah.
it's going to want to produce the heat. If I decrease heat, it's going to want to make heat. So it shifts to the right. If you don't understand that, there's a way to do it using the trough. Here's heat. If I lose it, it wouldn't be adding it, right? It'd be me taking a bucket and pouring water out, right? So if I'm pouring water out, there's going to be a shift to compensate for that loss in water to the right. So next week, those concepts of Le Chatelier's principle are going to be applied. And the bucket can help. The troughs can help. Now, you don't have to use that. I'm hoping it helps, but you don't have to use that.